Hello, welcome everyone. In today's lecture, we are going to be using the yield criteria that we learned in the last few lectures, basically the Tresca criteria and the von Mises criteria, to evaluate a structure and find out the factor of safety. So this kind of puts together everything that we have learned in the class so far. So essentially, we will be using the analysis of 3D structures under combined loading. Then we'll be using stress transformations. Then we'll be using failure criteria, using the stress transformations to find out whether a structure is going to fail or not, and whether it is going to have a factor of safety greater than 1 or not. So to be precise, what we'll do is we'll analyze the structure under combined loading and determine the factor of safety using Tresca and von Mises criteria. Okay, so let's look at the problem that we are about to analyze. So in this case, you have a shaft that is loaded in the following manner. Okay, so essentially the shaft is loaded by two pulleys, C and D, and the tensions on the two sides of the pulleys are given. Okay, so T1 is 2250 newtons, T2 is 1058 newtons, T3 is 3376 newtons, and T4 is 1588 newtons. Okay, so here the span of the shaft is given. So essentially the distance from A to C is 0.3 meters. From C to D is 0.5 meters. From D to B is 0.2 meters. And the coordinate system that you're going to use for analyzing the structure is given here. Okay. So now it's also said that this is a left side view. What does it actually mean? It means that you're looking at the structure from the left. Okay. So usually when you look the structure from the left, you draw the side view on the right. So essentially, that kind of tells you what are the kind of forces that are acting on these two pulleys and in what sense they're acting, whether they're acting in the positive z direction or the negative z direction or the positive y direction or the negative y direction. So in this case, the tensions T1 and T2 are acting vertically, basically in the minus y direction, whereas the tensions T3 and T4 are acting at an angle to the y-axis. Okay, or angle to the z-axis, whichever way you want to look at it. So if you look at it, the angle it makes with respect to the z-axis is 45 degrees. Okay, and these T3 and T4 essentially inclined up. Okay. Now, what else is given? It is said that the shaft is hollow with an outer diameter of 90 millimeters and an inner diameter of 50 millimeters. So essentially, this is not a solid shaft, rather that it is a hollow shaft. The second important thing that is given is that the yield stress of the shaft is 60 MPa, or more precisely, the yield stress of the material of which the shaft is made is 60 MPa. Okay? And now, given that the dimensions of the shaft are given, the loadings are given, you are asked to find out whether or what is the factor of safety based on the Tresca or von Mises criteria. So this is an example of a verification problem. So essentially, you are given the loads, you are given the dimensions of the structure, and you are asked to find out what is the factor of safety for this particular structure under this particular type of loading. Okay. So what we do when we start analyzing a structure like this is very similar to what we have done previously when we looked at problems under combined loading. First, we have to make sure that we know what are the internal moments and torques at every cross section inside the shaft. Okay, so that means that we have to draw the free body diagram, then we have to draw the shear diagram, then we have to draw the moment diagram, and also ultimately the torque diagram. Okay, so once we do that, we can calculate what are the normal stresses and shear stresses at the cross section where the bending moment or the resultant bending moment or the torque is maximum. It is only after that point that things start to change a little bit. That is where we'll start to use, again, the stress transformation equations that you learned before, and also how to use the failure criteria based on Tresca as well as von Mises. Okay? So let's just start with the basic stuff. So essentially, first we have to draw the free body diagram. So initially, I'm going to look at the XY plane. Okay? So I'm going to go through this a little fast because we have done many problems like this and you are very comfortable with this. Okay? So you draw the free body diagram in the XY plane. These are the forces that are acting. Okay, then you can use the force equilibrium and moment equilibrium to find out the two unknown reactions, AY and BY. In this case, AY turns out to be 13.5 newtons and BY turns out to be minus 15.6 newtons. Okay, what essentially it means is that By is in the opposite direction to the one that you have assumed. So it is not acting in the positive y direction, but rather it is acting in the negative y direction. Okay. So again, one thing I want to notice that in this figure, that is my x and that is my y. Okay. So that is how the coordinate system is given to us. Okay. Now once we have found ay and by, we can turn our attention to the xz plane so that we can find az and bz. Okay. So if you draw the free body diagram in the xz plane, that is how it will look like. There's only one external force due to the two tensions, T3 and T4, that acts on the xz plane. So the way to find out az and bc is a little bit simpler. And if you do that, you find that az is minus 702.02 newtons and bz is minus 2808.06 newtons. Again, what it essentially means is that we have assumed that az and bz are in the positive z direction, but it turns out that actually they are in the negative z direction. Okay. Again, this is the coordinate system under which we are analyzing the free body diagram in the xz plane. Okay. Again, this is something that you have done many times, so you should be fairly comfortable doing this. Okay. Now, once we know all the reactions in the xy plane and the xz plane, essentially you can draw the free body diagram with the correct sense of the forces. So in this case, ay is acting up because ay was positive. On the other hand, by is acting down. Okay, so I should probably have a positive sign here because I have already included the sense of the force in my free body diagram. The arrow is pointing down, so it essentially means that it's already negative. Okay. Now, the same thing can be done for the xz plane, and again, both the reaction forces az and bz are in the negative z direction. Okay. Now, once you draw the free body diagram with the reactions, you can easily construct the shear diagram. The shear diagram in the xy plane is going to look like that. Okay. And the shear diagram in the xz plane is going to look like that. Okay. So this is something, again, you have done many times. Based on the shear diagram, you can construct the moment diagram. The moment in the xy plane is mz, whereas the moment in the xz plane is my. Okay. And both of them are in Newton meters. Okay. Now, the shear diagram looks like this for the xy plane, and the moment diagram looks like that. Okay. And you can verify that the sense of the moment diagram is correct. It means that the sign of the moment diagram is correct. So if you take a cross section somewhere between A and B or B and C and whatever, and then you draw the free body diagram and find out whether the internal moment there is positive or negative, what you will find is that the internal moment that you find using the free body diagram agrees with the moment diagram that we have drawn here. So essentially that means that the moment diagram is correct as it is. We don't have to make any changes. Okay. On the other hand, if you draw the moment diagram for my based on this shear diagram, that is how your moment diagram will look like. Okay. However, if you draw the free body diagram and then find out what the internal moment my is at any cross section, you will find that it is opposite in sign to the moment diagram that you have drawn here. Okay, which means that you essentially have to flip the sign. So instead of having a minus 561.6 at point D, you are going to have a plus 561.6. Essentially, all you're doing is you're mirroring this moment diagram about the x-axis. Okay, and that is something that we have to do because the free body diagram tells us otherwise. Again, this is something that you have done multiple times, so I'm pretty sure you understand what's going on here. Okay, so now we basically have all the shear diagrams or moment diagrams. Now the next thing obviously to do is to find out or draw the torque diagram, because that is also something that is important to find out the maximum shear stress. Okay, so the torque diagram here is going to be actually fairly simple. If you use your right hand rule, you will find that the torque at point C is pointing to the left and the torque at point D is pointing to the right. So essentially, if you take any section between C and D, the free body diagram is going to look like that. Okay, so the torque TCD between C and D, the internal torque TCD between C and D is going to be pointing to the right. And since the TCD is in the same direction as the outward normal to that cross section, that torque is considered positive. So the internal torque between C and D is considered positive. Okay, and this torque TCD is going to be nothing but T1 minus T2 times RPC. So where RPC is the radius of pulley C. Okay, so this is something that you must keep in mind. So when you are finding the torque, you essentially subtract the two tensions on the opposite sides of the pulley and then multiply by the radius of the pulley. You don't multiply by the radius of the shaft. Okay, the torque depends on the radius of the pulley. Okay, so it's going to be T1 minus T2 times RPC, or for that matter, it's going to be equal to T3 minus T4 times RPD. Okay, and these two torques have to balance out each other because there are no external torque reactions. So the torque on pulley C has to be balanced out by the torque on pulley D. Okay, so essentially you can use either one, either T1 minus T2 times RPC or T3 minus T4 times RPD. Both will essentially give you the same answer. Okay, but anyway, that magnitude of that torque turns out to be 357.6 Newton meters. So the torque diagram is going to look like this. Essentially, from the point A to point C, it is going to be 0 because there are no internal torque in the cross section, in any cross section between A and C. At point C, you essentially have a jump in the torque, and then the torque remains constant all the way from C to D, and then it goes back to 0. Okay? And again, from the point D to point B on the shaft, the internal torque is 0. Okay? So essentially, now we have constructed the shear and moment diagrams, My and Mz, and also the torque diagram. Now, if you go back and look at the moment diagram, in this case, it's fairly obvious that the maximum internal moment is going to happen at D. Okay, so if you look at My at D, it is 561.6. That's a fairly large value. And the Mz value at D is also quite high, even though it is not the highest among all values in along the length of the shaft. It is still quite high. So in principle, you might want to find out Mr, the resultant moment, at both C and D, and then verify that the resultant moment at point D is the maximum. But in this case, it is actually fairly easy to figure that out. And if you find out the maximum or the resultant moment at point D, it turns out to be this value. Okay? So essentially, if you look at this problem, the torque, the internal torque is maximum all the way between C and D, whereas the resultant moment, which is the resultant bending moment, is maximum at point D. Okay, so this is where we would stop earlier. So essentially, we would find out the maximum resultant moment, the maximum torque, and then essentially use the formula sigma is mc over I and tau is tc over j to find out the maximum normal stress and shear stress in the cross section. But now we have to go a little further. Okay, and that is what we are going to see next. Okay, so the main thing that I want you to note is that we know what the resultant moment at point D is, and we also know the individual components of the moment. You know what My at D is, and you know what Mz at D is. Okay? And this is important because that will tell us how to draw the cross-section at point D and figure out what the neutral axis is and where the maximum tensile bending stress and the maximum compressive bending stress actually occur. Okay? And that is what we are going to look next. Okay? So now if you look at the cross-section D, I have drawn it in such a way that the normal to this cross-section is the positive x-axis. Okay? And now, based on that coordinate system, my z-axis will be pointing to the left and y-axis will be pointing to the top. Okay? Now, if you look at the moment diagram, the mz value at D is 561.6. Okay? And the my value is 561.6 Newton meters, and the mz value is minus 363.15 Newton meters, which means that the moment along the z direction is in the minus z direction. Okay? So if I draw my moment directions with the correct sign or the correct sense, my mz is pointing to the right. Okay? Because the z-axis is pointing to the left. The positive z-axis is pointing to the left. Similarly, my my is positive, so the my is going to be pointing up. Okay? So I didn't mean to do it that way. I just mean that this is my my. Okay? So My My is 561.6 Newton meters. My Mz is 363.15 Newton meters. So then I know what my Mr is that we have already calculated. Okay. And then we can find out what this angle theta is. Okay. So that is going to be just dependent on My and Mz. Okay. But the main point is that if my Mr is in this direction, then my maximum bending stress is going to be occurring at the points that are perpendicular to the direction. Okay? So P and Q are going to be the points in this cross section which have the maximum bending stress. Okay? Now, Mr is pointing in this direction, which means that if you use the right hand rule, you can find out that the point Q is going to be under compression and point P is going to be under tension. Okay? The bending stress, the magnitude of bending stress at both these points is going to be the same, but the value at point P is going to be positive, the value at point Q is going to be negative. Okay? So all these things we have done before. Okay. Now, apart from this bending stress, these points P and Q are also going to have a shear stress, and that is because of the internal torque that is acting on this cross section. Okay? And based on the torque diagram, the internal torque at this cross section is going to be in this sense. Okay? It is going to be counterclockwise. So the shear stress at point P is going to be in that direction, and the shear stress at point Q is going to be in that direction. Okay? And that comes from the direction of the internal torque. Now, this point P and Q both have high bending stresses, but they also have the maximum shear stress in the cross section. Okay? So what is this bending stress going to be? The bending stress is going to be in the x direction, because the bending stress is always along the axis of the shaft. So it is going to be sigma x. And that is basically the maximum normal stress in this cross section. Okay? And the value of that is going to be nothing but MRC divided by I. Okay? And this value of sigma x occurs at both point P and point Q. Again, this is just the magnitude. At point P, it is going to be tensile, which means that it's going to be positive. At point Q, it is going to be compressive, which means that it is going to be negative. Okay? So that is the normal stress in the x direction. Okay? The shear stress at point P and Q is not going to be just along the y direction or the z direction. That you can see directly, because if you look at the sense of the force at point P, it is neither in the z direction nor in the y direction. So it is going to have both a tau xz component like that, okay, and also a tau yz component or tau xy component. Okay, so that is something that I want you to really make note of. At point P and Q, sigma x is given by this value. Okay, but the tau is not automatically given by this formula. Okay, tau xy, there is going to be a component along the z direction, that is tau xz, and there is a component along the y direction, that is tau xy. Fortunately, this tau square is equal to tau xz square plus tau xy square. Okay, so even though we can't calculate tau xz and tau xy individually just using this formula, we at least know that the magnitude of the tau is essentially related to tau xz and tau xy using this formula. Okay, and that is something that we'll make use of. Okay. Now, so if you look at the points P and Q, you have at both points a tau xz and tau xy, and these are related to tau using the formula tau square is tau xy square plus tau xz square. And you also have a sigma x at both these points, the magnitude of which is MRC over I. All the other stresses at both these points are 0. So sigma y is 0, sigma z is 0, and tau yz is 0. Okay? So point P and Q are the most stressed points in the shaft, and we know essentially the normal stress along the x direction at that point, and we also know the magnitude of the total shear stress at that point, which is tau. Okay. Now, once we have all these things, we can start calculating what the sigma x and tau are. Okay. So for that, first we have to calculate the moment of inertia, the area moment of inertia, which is given by this formula here. And the polar moment of inertia is nothing but 2 times I for circular cross section. So in this case, your C that you usually calculate, that you use for finding out MRC over I, is essentially d outer by 2. So the outer diameter is 90 millimeters. So the farthest distance from the neutral axis is going to be d outer divided by 2. Okay? And d inner is 50 millimeters, and that is required to calculate this I and j. Okay? So if you make the calculation, you find that I is that value and j is that value. Okay? So now, once you know I and j, then you can find out what sigma x max is, and that is nothing but this is mr. So that is your C and that is your I. Okay? And that turns out to be 10.328 MPa. Okay? Similarly, you can find out what tau is. This is your internal torque T. Again, this is C and that is J. Okay? So essentially, you can find out what tau is. Okay. Now, I want to take a moment and kind of reinforce something. So if you think of the points P and Q, at point P, for example, you are going to have a normal stress, sigma x. Okay? And the value of that normal stress is that. Okay? In addition, you are also going to have a shear stress. Okay? There is going to be a tau xc and a tau xy. Okay? This tau xz and tau xy, we can also evaluate independently from tau, but we don't need to do that. But the main thing is that we know that the tau square is tau xy square plus tau xz square. Okay? And that tau is this value. Okay? So that is the state of stress at point P. Okay? The state of stress at point Q is very similar, except that instead of the sigma x being positive, sigma x is going to be negative. Okay, that's it. Okay. Now, once we have all these values, sigma x and tau square at point P and point Q, then you can find out tau max. Okay, this is something that I really want to take some time to explain. So, all these years, you have been taught that the maximum shear stress is Tc over J. That is only strictly correct for shear stress on the cross section. So essentially, if you have a shaft and you take a cross section, then the maximum shear stress on that cross section is Tc over J. That is not the maximum shear stress in the entire shaft. Okay, that is something that you really need to understand. Okay, now how are you going to find out what this tau max is? Okay, the tau max is actually going to be given by this formula. Okay, and where that comes from, if you recall, your tau max for a 2D stress state is given by square root of sigma x minus sigma y divided by tau the whole square plus tau xy square. Okay, that is what we learned for 2D stress transformations. Okay, in this case, this tau xy square is nothing but tau square. Okay, and this is just sigma x by 2 the whole square because sigma y is 0. So that's why I kind of went back and talked to you about this. Okay, so this point P has only one normal stress, sigma x. It has two shear stresses, tau xy square plus tau xz square. However, if you do a rotation of the coordinate system, you essentially can go from this 3D stress state, because you have both a component in the y direction and the z direction, to a 2D stress state. Okay, and in that case, this is going to be your tau max. Okay, so tau xy becomes actually tau, and tau max is going to be sigma x squared, sigma x by 2 the whole square plus tau square. Okay, so again, I'm going to actually do this one more time once we go through the whole thing, because this is a point of confusion for a lot of students. Okay, but for a moment, let's assume that tau max is this value. Okay, and you can calculate what the value of tau max is, and that is the maximum shear stress at any point on the shaft on any plane. Okay, it is not just the maximum shear stress in the cross section, it is the maximum shear stress in any plane that you can think of in the shaft at any point in the shaft. Okay, so once you know tau max, then you can calculate what the safety factor based on Tresca is. Okay, we know that the safety factor of Tresca is nothing but sigma y divided by 2 times tau max. We are already given sigma y, and we know what tau max is now, and we find out the safety factor is 5.123. Okay, and again I want to make a note that sigma y is nothing but sy. So these symbols are often used interchangeably. So sometimes they denote the yield stress as sigma y, sometimes they just denote it by sigma y or sy. Okay, so essentially sometimes you have both the symbols. So anyway, in this case, the yield stress is 60 MPa. So now your N is 5.123 MPa, 5.123. Now, let's now look at the von Mises criteria. Okay. Now, if you look at the von Mises criteria, essentially the material yields when sigma von Mises equals Sy. Okay, that is the von Mises criteria. And what is this von Mises stress? It is a fairly long expression. So it's half times sigma x minus sigma y the whole square plus sigma y minus sigma z the whole square plus sigma z minus sigma x the whole square plus 6 times tau xy square plus tau xz square plus tau yz square. Okay, so that is the expression for sigma von Mises, right? Now, in this case, sigma y is 0, sigma z is 0. Okay, so these are all 0. And tau yz is 0. Okay, now what happens? Essentially, you get sigma x square plus another sigma x square. So that is the 2 sigma x square here. Okay, and now you have 6 times tau xy square plus tau xz square. What is tau xy square plus tau xz square? That is nothing but tau square. Okay, so essentially now you can find out, you already have found out what the value of tau is. So you substitute that in this expression. You already know what sigma x is. You substitute into that expression. You find sigma von Mises to be equal to 11.38 MPa. Now the factor of safety is going to be nothing but Sy over sigma von Mises, or sigma y divided by von Mises, and that number turns out to be 5.272. Okay, so the safety factor based on von Mises criteria is a little bit higher than the safety factor based on Tresca criteria. And this is not surprising because the Tresca criteria is more conservative. So it is always going to give you a safety factor that is lower or at the maximum equal to the von Mises safety factor. So if you come up with an answer where the Tresca safety factor is more than the von Mises safety factor, that automatically tells you that you have made a calculation mistake somewhere. Okay, so that is something that you can always keep in mind. Okay, so the only thing that I want to kind of again emphasize is that when you have a point like P or Q, the stress state at that point is not strictly two-dimensional based on the coordinate system that we have. So at point P, you are going to have a sigma x, you are going to have tau xz, and a tau xy. So it appears like it is a three-dimensional stress state. However, if you rotate the coordinate system about the x-axis, so that, for example, your y prime axis is like that, and your z prime axis is like that, then you can essentially make that 3D stress state into a 2D stress state. Okay, and once you make it a 2D stress state, this formula is applicable. So essentially, your sigma x is still sigma x, sigma y prime is 0, sigma z prime is 0, and tau xy and tau xz essentially becomes just tau, which is going to be in this case tau xz prime. Okay, So essentially, you can take the two shear stresses that are acting along the y and z direction and make it into one shear stress that acts along the z prime direction. So essentially, then you can use the 2D stress analysis equation that we derived earlier. Okay, and that is how we are able to use this expression here. Okay, so again, this is a lot of material. There is a lot of new things that you are trying to apply, and you are trying to essentially use all the concepts pretty much that you have learned through this class in a single problem. Okay, so I want you to kind of make sure that you understand each of these concepts, and then that will help you with solving the problems in the associated homework. Thank you.